Here we go. Just a little bit about the Chapter 5 material to begin with. This is what we call discrete probability distributions. 5.1 introduces the general notion of a discrete probability distribution, as well as some basic facts and functions. There's some keystroking involved. And then section 5.2 takes a look at a very specific type of discrete probability distribution called a binomial probability distribution. All right, so let me go ahead and begin in 5.1. Oh, the title there is Basic Concepts. All right, and I'll offer up examples as we go through the discussion. First up, a random variable. A random variable. Usually the letter X. It has a single numerical value. And this numerical value is determined by chance. And that is by chance for each outcome in a procedure. And before I go any further, let me just offer up a couple of, or offer up a very specific example. And this is going to actually enable us to tie together material from chapter 2, chapter 3, and chapter 4. So we've got a fair coin. We're going to flip that coin 2 times. All right, the sample space, very straightforward, heads, 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 tails, tails, heads, and tails, tails. You've seen me use this sample space quite a bit for simple examples. So we're going to flip a coin 2 times. There's our sample space. My random variable for this particular example, the random variable here is X, and X is going to be equal to the number of heads. So if I take a look at my sample space, I can see that there's only a handful of values that X can even take on for this particular example. I might have 0 heads. That's when I get 2 tails in a row. I might have 1 head. That's where I get first a head and a tail, or perhaps a tail and a head. And then there's a way I might actually end up with 2 heads if I flip the coin twice and it lands on heads both times. So there's my random variable. And it's got a single numerical value determined by chance. These guys here are the numeric values. And they are determined by chance. For example, the probability of 0 heads is 1 out of 4 flips, or 1 out of 4 possibilities. Excuse me, I'm taking that directly from my sample space. There's two different ways out of the 4 to get one head. So it's got a probability of 1/2. And finally, to get 2 heads, again, it's 1 out of 4. So the chance part here is the 1/4, the 1/2, and the 1/4. The numeric values are the 0, the 1, and the 2. That's an example of a random variable, and it's an example where it takes on a particular value. There's a probability that it'll take on any one of those given values. So there's the first part. Now let me remind you of a definition or two that we looked at quite a while ago, and I honestly don't expect people to really remember. Maybe vaguely, that'd be nice. Probability distribution. I believe I mentioned this back in chapter 4, but honestly, if you don't remember, that's okay. And all this does, it gives the probability for each outcome. For example, we had X and we had P of X. We had a 0, a 1, and a 2. 0.25, 0.5, 0.25. So there's an example of a very basic probability distribution. Sometimes we use formulas, sometimes we use tables, sometimes we can use a graph. For example, we have something like a histogram where we've got the probability here. It's different than the ones we were a little bit different than the ones we were looking at previously, although the things that we use there can be made to work. I'll just go ahead and I'm not going to dwell on this overly long 0, 1, 2. So there's the 0.25, there's the 0.5. And as I say, there's a couple of different ways of going about doing these kinds of things. There's a formula depending on what we're looking at, a formula approach, if you will. But that's really a probability distribution. The idea is you've got, and this is the important part here, you've got outcomes and probabilities. So you can associate each probability with a particular outcome or each outcome with a probability, which is probably the correct way to say it there. In any case, there's our probability distribution. Now, if that wasn't going back far, let me go back even farther, way, way back to I think it's chapter 1. I'm going to remind you of a couple of very basic variable types. We have a discrete random variable. And we introduced this notion of discrete back in chapter 1, discrete random variable. And if you take a look, and if you take a look at the book, I'll let you read the definition in the book. Here's basically what we mean by discrete random variable. We have a finite or countable number of outcomes. For example, something that is discrete. I'm going to give you some very basic ones. We took a look at a couple of these in chapter 1, discrete. Shoe size, coin flips, dice rolls, gender. So for example, shoe sizes. You might have something like an 8, an 8.5, a 9, and so on and so forth. You have nothing to choose from between an 8 and an 8.5. You've got to make do with either an 8 or an 8.5. You only get so many shoe sizes. Coin flips. It could be, for example, the number of heads, depending on the number of times you flip your coin, like the example we've been looking at. Number of, well, I don't know, boxcars. What are boxcars? Boxcars are when you get 2 6s in a row. Those are boxcars. Gender, maybe the number of girls in a randomly selected group of birds. So these are all examples of objects that are used or counted with these notion of discrete random variables. Honestly, we will look in this particular chapter, we will look a lot at these kind of things right here. Not so much the shoe size, although I suppose someone might try to make a problem up like that. Probably not me. And then the discrete random, by the way, before I go any further, discrete random variable, discrete, it's chapter 5. Chapter 5 is all about these discrete random variables. The discrete random variable has a brother, or maybe sister. Continuous random variable. Continuous random variable. These can take on any value in an interval in the fashion of your algebra course. Very common ones are things like height. And time. If you're taking a look at height and time on your x-axis, height on the y-axis, what do? People grow up. They start at a particular height, they end at another height, and you don't lift your pencil while you draw that graph. That's an example of continuous random variables. Other things are most physical quantities, things like weight. And let's see, we got height, time, weight, other things, distance, which in some sense is the same thing as height. But in any case, these are examples of continuous random variables. And these continuous random variables are what we look at in chapter 6. Our calculator has different tools for working with discrete versus continuous random variables. So it will be important to distinguish variable type. Otherwise, problems become unwieldy. There's a couple of facts about any probability distribution. And I'm going to put my coin toss example back up here. There's my distribution. For all x, the probability falls somewhere between 0 and 1. And you'll note that my probabilities these values here all fall between 0 and 1. If I add up my probabilities, they sum to 1. So the sum of those probabilities must equal 1. Finally, each outcome has its own category. Category or class, just like in chapter 2. So each outcome has its own category. Class, and what was that other one? Oh yes, the probabilities sum to 1. And there we go. Excuse me. That is the basics of any probability distribution. Now, excuse me. Each probability distribution has parameters. And if you take a look at your book does something that's a little bit funny. First, we have the mean. And then I'm going to do a couple of examples to really drive home the point that you guys actually can bring a little bit of intuition to this. So the mean is the essentially average outcome. If you want to think of it like that, you'll be doing just fine. I'm going to give you a formula. It's in the book. I honestly don't really expect students to use this. I think I'll use it a single time. And then I'll show you how to use your calculator to actually find these values. So we have the mean. And note that, I make a big deal about vocabulary throughout the semester. It's a very important topic. This word parameter was introduced to students back in chapter 1. It's one of the very first of our vocabulary words. And it refers to a population value, or a value that's applied to an entire population. And I'll remind you that we used Greek letters. And this is the Greek letter mu, M-U, mu. So we interpret a probability distribution very much like population data. We have the mean, we have the standard deviation. I'm going to put the formula up here. And I'll remind you that that basically has some sort of square root in here. This one is much more difficult to use as opposed to the formula for the mean. And one of the reasons we like our calculator. And then your book uses a couple of different formats for the variance. And one of them is kind of interesting. It's referred to as the one that is easier for calculators, but it's really easier for calculators that are not good calculators like our calculators. So I don't really worry about both of them. I just really take a look at the two of them. I'll remind you also, again, that we've got these Greek letters in play here. If you remember, that Greek letter that we're using here is sigma. I'm going to run through this example using my very simple probability distribution for coin tosses, for a couple of coin tosses, just to see how the probability distribution works. But before I do that, I'm going to ask you all to go out on a mental limb and ask yourself to answer the question, well, if you're going to flip a fair coin twice, about how many heads should you see? Remember, we've got two flips. So my mean is equal to x times p of x. I have to add them all up. So x times p of x, that equals 0 times 0.25 plus 1 times 0.50 plus 2 times 0.25. So my mean is equal to, this one goes away, I get a 0.50 plus another 0.50, because 2 times 1/4 is 1/2. I have a mean of 1, and I'm going to throw in a single decimal place for rounding. So one head in 2 flips. Does that make sense to people that you should see on a fair coin about 1 head and 2 flips? Of course it does. Now, let me go ahead and switch to my calculator, and I want to start doing these keystrokes on my calculator. And this is actually a very good example to start with. So let me share my screen. Let me find Mr. Calculator. There he is. There we go. All right. So the first thing I will note about my data is I really need now 2 columns for my data. Let me clear out column 1. And I've got column 1 and column 2. Column 1 has the outcomes, the x values, the 0, the 1, and the 2. Column 2 has the probabilities. So I've got values in column 1 and in column 2. I still want to calculate my one variable stats. I have my calculator set up like this. I'm going to do it the other way also. Second, L1, and now this is most important if your calculator looks like this. You need a comma. Without the comma key, that's right up above the 7 key, the calculator will just blow chunks. It just won't work. Second, L2. Now you hit enter. And I'll call attention to the fact that my calculator is incapable of working with a mu in this situation. It still thinks it's got a sample in some respects because I see an X bar, but I really know that that's not X bar. It is mu. Also, I note as I scroll through, if I scroll through my output, my usual standard deviation S is not there. It is entirely blank. But I've got my sigma. I'm paying attention to that notation. So I've got a standard deviation of 0.707106 and change. And I get all the other stuff I usually get with my one variable stats. Minimum, median, Q1, Q2, Q3, max. So we get them all. But what I'm really interested in is the mean, the standard deviation, and the variance. So you can't see me, but right now well, maybe you can. I'm going to write down the mean, 1.0, and my standard deviation, 0.707 and change. If I want one decimal place, I look to the second one to tell me what to do, 0.7. We are talking about heads, so I will note the units. Now, the last thing I really need is my variance. The variance is the square of the standard deviation. And I really want all my decimal places. Let me clear my screen and go over these keystrokes. I went over them in chapter 3, but it's been a little while. I didn't use them in chapter 4. My calculator just got done doing some one variable stats. I recognize the sigma x. I can take that sigma x. I can look at it if I want. However, I don't really want to look at it. I want to, and then I'll use my handy x squared key right over here. This is the value that I have. I want one decimal place. Look at that, 0.5 heads squared. Okay, so let me stop my sharing there and point out that the mean, 1.0 heads. Standard deviation, 0.7 heads. And the variance, 0.5 heads squared. So we've got, excuse me, we've got the data in there, in our example anyway. And those are the, what do we call them? Remember, we call them parameters. Okay, let me actually run through one more example. And this time we're going to work with 4 random births. We're going to let x equal the number of girls. Now, I'm going to give you the distribution. I'll show you in the next chapter how we actually develop it. But if we're talking about the possible number of girls in 4 births, it's possible there might be 0, maybe 1, maybe 2, maybe 3, maybe 4. Anywhere in that category. So 0.0625, 0.25, 0.375, 0.25, 0.0625. Don't worry about how I came up with those probabilities so quick. I will indeed show you how to find them eventually, so don't stress on that. It is a probability distribution. All of these fall between 0 and 1, and when I add them up, they add up to 1. So now, if you're picking 4 burrs at random and you're looking at the number of burrs, on average, how many do you think you might see? You know how babies work, pretty much 50-50, right? I will note that the 2 girls and 4 burrs has the highest probability of occurring. So what we're going to do is we're going to use this data, where we are going to find the mean, the standard deviation, and the variance. We're going to round these almost exclusively. I'm just not sure how weird our book gets from time to time, but I'm pretty sure everything in chapter 5.1 gets 1 decimal place, because this is the variable we are interested in. It has no decimal places, so I'll be taking 1 decimal place here. So this is the value that these are the values that have to go in to my into my calculator. So let me share my screen again. Let me go back to edit. Let me clear 2 lists. Clear. Go away. So 0, 1, 2, 3, 4. Down on the other side, 0.0625, 0.25. Oh, sorry. 0.25, I said. There we go. 0.375, 0.25, 0.0625. So they're all in there, list 1 and list 2. Go right to stat. Excuse me. Pick up the 1 variable stats. Second list 1, comma, second list 2. Blow on it once for luck, hit enter. So there's the mean, there's the standard deviation. This is kind of interesting. The mean is 2. I certainly would expect 2 out of 4 babies to be girls. That's the most common outcome anyway. No S, but I've got a standard deviation of 1. That means that with no decimal places, sure, I can use my vars key, but there's really no need to. It's just 1 times 1. So let me note these. Then I want to try my other keystrokes again. So mu is equal to 2.0 girls. The standard deviation, 1.0 girls. The variance, 1.0 square girls. So there we go. So I've noted that. Let me clear this. And if my calculator is in the mode where the stat wizard is on, now when I go to my 1 variable stats, I see this. So this one, I honestly do not use this one very much. Let me see what happens when I put list 2 here. Let's see. Let's calculate. Yeah, list 1 and list 2 goes in just like that. So the frequency list is list 2. The outcome list is list 1. But there we go. Let me stop my sharing. Hold on, I've got to pause for just 1 moment. Sorry about that, I'm back. So there we have the basics of probability distributions. Now, let me talk a little bit about how we like to use these probability distributions. And I'm going to use this one right here in front of us. So what? So, so this is a place where the language can get tedious. I need that table back, so I'm going to recreate that table. 0, 1, 2, 3, and 4. 0.0625, 0.25, 0.375, 0.25, 0.0625. And by the way, if you are wondering, the distribution does approximate a normal distribution. It's very bell-shaped. So the questions here that you're going to run into are questions that are like this. What is the probability and I'm going to give you a couple of different examples of exactly one girl. Exactly one girl. Probability of one girl. I can go right to my table and read that off. 0.25. Of more than one girl. More than one girl. That must mean 2 or 3 or 4 girls. This is a place where I've got to add up 0.375, 0.25, 0.0625. I'll come back to that in just a moment. More than, how about if it was at least one girl? This was more than, this is at least one. At least one, 1, 2, 3, or 4. Basically, I'll have to sum all of those up, everything except the first one. By the way, it might have been easier to subtract that first one from 1 and do it like that. In any case, the language is tricky. But the arithmetic is really not bad at all. For example, 0.375 plus 0.25 plus 0.0625. What did I get there? 0.6875, and then I can round that if I need to. This one here, 0.25 plus 0.375 plus a 0.25 plus a 0.0625. And I get a 0.9375. What I'm really trying to stress here is the fact that, 2 facts. Number 1, the language is absolutely vital. I know it bothers students a lot, but it is absolutely vital. Also, the actual numbers are already here. We just really need to add up the correct ones, and that happens when we interpret these kind of statements correctly. So that's something to keep in mind. Now, I'm going to dip back, and I think this will probably take us to the end of our time, a little ways, and talk about significant numbers of outcomes. All right. We have a probability value. If the probability of whatever it is we are looking at is less than or equal to 0.05, whatever we're looking at is significant. Maybe high, maybe low, we don't know, but it will be significant. We got to actually look a little bit more at the problem. The important component here is that 0.05. This number here is kind of set in stone for us this semester for identifying significant outcomes. So, we have what we call a significantly high number of successes is at least X if the probability that X is at least some particular value, I'll show you what I mean in a moment, needs to be less than or equal to 0.05. 0.05, put that 0 in. If at least X successes, that's what I mean here. So, let me give you an example. And the same goes for a significantly low number of successes. And most 0.05. So it's very, very similar to what we were looking at before. Let me give you an example. If I go back to that previous example, using the I'm going to just put in the 2 at the end. You'll notice that both of these values are greater than 0.05. So neither one of these would be not significant. On the other hand, and again, you're not going to know where I'm coming up with these numbers. I will show you eventually. If we flip a coin 10 times, if we get 3 or fewer heads, that's low. And I really do need to know what that value is, and I can find that value pretty quickly because I've got some special tools that you guys don't have in front of you right now. Oh, I was wrong. Heavens. Oh, bad. I'm gonna have to change that. I'm messing around here off camera. Yeah. Almost there. If this was a face-to-face class, yeah, so 0, 1, or 2 is equal to 0.0547. On the other hand, the probability of 0 or 1 heads in those flips is that was quite a bit smaller. 0.0107. So, and again, I'm going to show you where I come up with these values, just not tonight, because that's not the point of this particular discussion. So this one here, this would be x equals 0 or possibly 1. You notice that probability of 0.0107. That is less than 0.05. So if I were to flip that coin 10 times and got 1 or fewer heads, that's way low. If I got 2 or fewer heads, you can see that this number is just a bit higher than 0.05. That would not be a significantly high number of heads. In any case, we're just about out of time, but that does bring you up to the end of 5.1. Your calculator is going to be really useful in 5.2. I'll introduce a new tool for working with a specific type of distribution. Let me go ahead and stop the recording.